Now we're going to move on to Alex West. So Alex is based at the UK Met Office Hadley Centre and works on sea ice model evaluation and development and sea ice monitoring. So his presentation today is on CMIP 6 overestimate Arctic sea ice growth, melt and conduction relative to ice mass balance buoy measurements. So thank you very much, Alex. If you're able to share your presentation.
Yeah. Okay, can people see that?
Not yet.
So I've shared my screen, at least tried to. Hang on a minute. Is that any better?
Yes, we can just see it just needs to go into presentation mode. Perfect.
Great. Thank you. Okay, so yes, I'm going to be comparing sea ice in CMIP 6, specifically energy fluxes of melt growth and conduction to some in situ measurements. Yeah, so I'm going to use these devices called ice mass balance buoys to evaluate fluxes. As you all know, there are a very large number of CMIP 6 models, over 100, I think, and only about 17 produce the diagnostics required for this evaluation. And like CMIP 6 as a whole, they represent a very wide range of Arctic climate states, from sea ice that's very thick to sea ice that's very thin. Why is it helpful to look at sea ice growth and melt? Well, we're very interested in sea ice area and volume, and this is very closely coupled to ice growth and melt. Obviously, the growth and melt drive area and volume, but the causality goes in the other direction as well. Thicker ice tends to grow more slowly than thinner ice in winter because it conducts energy less effectively from the warm ocean to the cold atmosphere. And in summer, thinner ice tends to melt more than thicker ice because it's darker. Open water tends to form in areas of thin ice more readily, allowing solar energy to be absorbed more quickly. And you do, in fact, see this come out pretty quickly in the ensemble evaluated, in that thicker ice models tend to have higher fluxes than thin ice models. But this varies slightly depending on the internal ice thermodynamic parameterizations, and there is a bit of a model bias that will come out of this. Just talk briefly about how sea ice tends to be modelled in CMIP 6. I think virtually every model now has some sort of sea ice component because it's obviously very important in modulating the energy fluxes between the atmosphere and ocean, but they're not all equal. And the models that provide the right diagnostics from this study tend to be among the more sophisticated. They include things like a subgrid scale thickness distribution. So each grid cell doesn't just have a block of sea ice. It models different sorts of sea ice, usually in separate so-called thickness categories, which evolve separately because they tend to be governed by slightly different physical relations. They have a quite sophisticated sea ice dynamics in that they have internal sea ice stress terms. The sea ice isn't allowed to float freely. And which is most important for this study, they tend to have quite complex sea ice thermodynamics as well. The thermodynamic solver will tend to calculate ice growth and melt based on the energy balance at the top and basal surface. And all models which are assessed in this study have ice and snow heat capacity. They calculate new internal temperatures at each time step. But they vary in a few ways as well that'll be relevant. Some models allow sunlight to penetrate through the ice, others don't. Models treat ice salinity in different ways. This affects the thermodynamic properties of the ice. Some models completely prescribe it. Some models allow it to evolve. Sorry, it's not completely showing at the bottom. They allow it to evolve in bulk, but they have a prescribed vertical profile. Some models allow it to vary in 3 dimensions, and the most complex models, so-called 3D prognostic plus mushy layer, you probably won't be able to see that right at the bottom because my taskbar is hiding it. But basically, these models have a layer at the base of the ice that's a mix of ice and seawater, which would be quite important, as we'll see. Obviously, they vary also in the number of layers they permit. And they have different ways of treating melt ponds as well. Meltwater that forms on the ice in the summer. Some of them parameterize it. Some of them model it explicitly in various different ways. I'll just show briefly why this is particularly important. I mentioned that there's a very large spread in sea ice states in CMIP 6. You can see a representation of it here. The green bars on the right of these diagrams show the spread in CMIP 6 sea ice states. Very widespread, a lot of them outside observations. It's also, I think, relatively well known that models tend to underestimate the sensitivity of sea ice to global temperature change. So I'll be evaluating these models with ice mass balance buoys. I'll just talk briefly about what these instruments are. They are systems of instruments frozen into a sea ice flow. You tend to have acoustic sounders, which measure the elevation of the top and the basal surface of the ice. And you have a string of thermistors through the ice, which measures the internal temperatures. About 100 of these instruments have been released in the Arctic since the early 1990s. You can see here a map of where they tend to be located. They're mainly, at least the ones with publicly available data, are mainly in the North Pole and the Beaufort Sea regions, and they don't tend to last very long. But overall, they give us quite a good sample of these areas. And importantly, you can, in principle, use these measurements to calculate fluxes of melt and growth from the acoustic sounders and of conduction from the thermistor string. And this is what I did in Westertel 2020 to try and compute a data set of these fluxes for these two regions and use them to evaluate the Met Office model in this study. So there are 17 CMIP 6 models that produce the diagnostics we need. I've got here a couple of graphs showing the annual mean sea ice thickness in these 17 models. We'll see what they are in a minute. Plotted firstly in the top against September sea ice area, how much the sea ice melts back in the summer. This is for the historical runs, 1985 to 2014. You can see, as you expect, there's a relatively strong positive correlation between annual mean ice thickness and September ice area, albeit with variation within that. And here it's plotted against the amplitude of the sea ice thickness at seasonal cycle. I mentioned earlier that intrinsic sea ice feedbacks tend to mean that thin ice grows and melts more than thicker ice. So you would naively expect to see a negative correlation here, which at first sight is lacking. This is mainly due to these clusters of models down here, which I'll talk more about in a bit. They have quite low annual mean ice thickness and quite a low amplitude of the ice thickness seasonal cycle. So you can divide these models into groups, which I'll just briefly talk about. First of all, these two ones at the top here, the IPSL group, which there are two. These use the LIM3 sea ice model. It's got a salinity scheme of intermediate complexity. Bulk salinity is allowed to vary. It does allow solar radiation to penetrate into the ice. The melt ponds in this model are just parameterized. This is quite a warm model. Sea ice melts and growth are quite high, but the ice thickness is perhaps not quite as low as you might expect given these things. It's quite close to the estimate of the biomass forced ice ocean model, which is often used as a reference for ice thickness, although it too has relatively wide uncertainties around it. The blue dots are the so-called GSI 8.1 group. These use the GSI 8.1 sea ice configuration developed by the Met Office. This is SICE 5.1.2, which is perhaps unique. These are the models that don't have penetrating solar radiation in summer, or the sunlight is absorbed at the surface of the ice. And these models tend to be quite cold. They have quite a low global average temperature in this period, and their sea ice, as you can see from this graph, tends to be quite thick. And there's quite a pronounced negative correlation between thickness and growth and melt, as you would expect. There's the mushy layer group. these are the purple models here. They've got quite widely varying climate states with the correlations that roughly that you would expect. This is a different configuration of size 5.1.2. It does model solar radiation into the ice, but it's also got this so-called mushy layer at the base of the ice, a mixture of ice and water, basically. There's a single model from MRI, that's the pink dot. This is interesting because it's completely independent of all the other models. There's no common code at all. But in some of its thermodynamic choices, it's similar to LIM3 and gelato. However, there is only one ice layer. Salinity is prescribed. And this model is particularly close to observations for all evaluated models, variables. The brown dots are the CMIP Surfax models. They have complexity similar to the IPSL and MRI group. These tend to be quite warm with thin ice, but as I mentioned, their melt and growth is surprisingly muted. We'll see why in a bit. And finally, there's the CMCC group, the green dots over here, the two models. This is an earlier version of SEIS. These models are very, very warm. Their sea ice is very thin. And in fact, the reason they don't have a lot of growth and melt is because the sea ice melts out completely in about July. So it's bounded below, if you like. So that's what these models look like. We'll now have a look at how they simulate ice melt and growth fluxes and compare these to the ice mass balance buoys. So I mentioned there was these two regions that are particularly densely sampled by the buoys, the North Pole on the left and the Beaufort Sea on the right. So what we do, we look at all the buoy measurements in these regions for each month, aggregate them into a distribution. This distribution is shown here by the black lines, which show the median, and the grey regions, which show you the interquartile range in these cases. Certain months you get a slightly more detailed view of the distributions, with the full ranges too. And for each model, we look at all the grid cells in these regions for each month and use these distributions to compute statistics, which are weighted obviously by grid cell area and ice area. And comparing these, just looking through each of the model groups in turn, the CMCC models, these are the green lines, they tend to be very amplified, much higher top and basal melting than observations. And this is interesting because it's physically consistent with what we expect based on these models being very warm and thin. They, of course, have much higher ice growth in winter as well. Again, that's what you expect when you completely melt out all your ice in the summer. It initially grows again very quickly. The CNRM Surfax models, these are the sort of browny beige ones, they're also quite amplified and they're also phase shifted. For example, you can see here for top melting, they tend to attain their maximum top melt in September. And this is not at all what we see in the observations or indeed in any of the other models. The same is true to a lesser extent for the basal melting. It's slightly phase shifted earlier, and the basal growth is phase shifted much earlier. So it attains its maximum in September, like the top melting, in fact. And this is why, incidentally, that these models don't show a large amplitude of sea ice thickness, despite being quite thin, because their top melting and basal growth tend to occur at roughly the same times of year. It's quite net neutral for the ice thickness. And we've spoken to the model owners about this, and they think that there is actually a problem with the models here, and that's why this happens. Moving on to the ones that are close to the observations. The GSA 8.1 models, these are the blue ones. These are quite interesting as well because the top melting is quite amplified. It's a lot bigger than we see in the buoys, despite these models having quite thick ice, being quite cold. But this isn't so much the case for the basal melting. It's a lot closer to the ice mass balance buoys here. And again, this is consistent with these being the only models that don't allow sunlight to penetrate into the ice. It's all absorbed at the surface, and we would expect this to cause more top melting relatively and less basal melting. They also tend to be, incidentally, to be relatively amplified growth in the winter, which again is interesting, given that they probably have quite thick ice, because this isn't necessarily what you would expect. The mushy layer models, the purple ones, these tend to be closer to the ice mass balance buoys in all respects. Again, perhaps growth slightly amplified on average, although this is not the case for every model here. The IPSL models, they're kind of intermediate. These are the red lines here. They are slightly amplified, but less so than for these top two groups. MRI is quite close to IPSL in terms of its basal melt, the pink line here, but it is closer to the ice mass balance buoys for top melt and basal growth, and incidentally the mushy layer models. But viewing this as a whole, we can see that there is tendency for these fluxes to be higher than the buoys measure rather than lower, perhaps the first tentative signs of an overall model bias. We'll now have a quick look at the conduction fluxes. These are very important because it's conduction through the ice from the warm ocean to the cold atmosphere that drives ice growth during the winter. It's an important driver between the overall sea ice state. This is exactly the same way. North Pole region evaluated on the left, both at sea on the right. The top row is the top conductive flux, how the atmosphere is exerting its thermal influence on the ice. And the middle row is the basal conductive flux. It's what the ice bottom surface sees and what drives sea ice growth. And of course, in models that don't have sea ice heat capacity, these two fluxes are the same, but all the models evaluated here do, so they're different. And the basal conductive flux, for example, in the buoys, is a lot more damped and phase shifted a lot later in the year compared to the top conductive flux, as we would expect, the effect of the sea ice thermal inertia. Just going through the groups in turn, CMCC are again very amplified, what we expect from the thin ice. The CNRM Surfex models are also amplified, and they're phase shifted. The GSA 8.1 models, they are less far from the buoy observations in the first two groups, but they have some interesting characteristics, particularly the top conductive flux. You can see that it actually reverses too much in the summer. It becomes too strongly positive compared to the ice mass balance buoys. Again, this is consistent with more energy being absorbed at the top surface of the ice. The mushy layer models have much lower basal conductive flux than the rest of the models evaluated here. Again, these models work slightly differently at the base of the ice. They have this layer that's a mixture of ice and seawater. We've spoken to the model owners about this because it really is very striking. And in fact, it produces some results which, have taken at face value, aren't entirely physical. But the model owners tell us that there are actually a couple of missing terms in the heat budget at the base of the ice due to this special way of modelling. So while this is an accurate representation of the conductive flux, you can't necessarily use this to derive other variables in the same way that you might the other model groups. MRI and IPSL are interestingly very similar to each other in terms of this, despite having completely independent code bases. But again, some of their thermodynamic choices are similar. They're also probably overall the most similar to the ice mass balance buoys, although still slightly too amplified in winter. Again, you can see that in general, during the winter, the models tend to have a lot more conduction than is measured by the ice mass balance buoys. So I'll just point out, this is particularly bad in the early autumn. You can't take this at face value because buoys tend to be preferentially frozen into regions of thick ice, which, well, I say thick ice which isn't very thin, which will tend not to grow as quickly because the scientists who deploy these buoys tend to not like them melting out too quickly because they're quite expensive to deploy. So in order to have a fairer comparison, we're going to evaluate these fluxes as a function of the ice thickness. So what we've done here, this is the top conductive flux in winter in the Beaufort Sea region. I'm showing this as an example. What we've got, all the black dots are the ice mass balance buoy measurements. You've got the average ice thickness measured for that month on the x-axis and the conductive flux measured for that month on the y-axis. And then what we've got here, I haven't plotted all the model grid cells in these regions because there are tens, sometimes hundreds of thousands of them, and it would be unreadable. What I've done is taken a random sample of 100 grid cells for each model, again, with probability of selection weighted by grid cell area and ice area. And this gives you a scatter plot that allows you to see that even as a function of ice thickness, when you restrict it to these intermediate categories that are sampled by the buoys, there is still a model bias present here. The models tend to have stronger conduction than you see in the buoys. And this is also true for other fluxes. For example, when we look at the top melting flux in July here, the buoy distribution is again offset from the model distribution as a whole, although not perhaps each individual model. Finally, I'll just point out that even this isn't a perfect comparison because each model grid cell has this sub-grid scale thickness distribution that I mentioned at the beginning with ice of different thicknesses. And this matters because a grid cell of average thickness H will tend to conduct energy more efficiently than a single ice flow of thickness H because the conduction varies much more for lower thicknesses. The relationship is non-linear. Now, it turns out you can actually allow for this effect for those models that provide the ice thickness distribution data, the area and thickness of ice in each category. Not all of them do, only 6 do. I've got them down here. But basically, I've got here the same graph as up here, using the grid cell mean ice thickness to estimate the thermal insolence, the tendency of the snow ice column to block energy. And you can transform this to a point value equivalent, effectively moving this whole distribution to the left, allowing them to transmit energy more efficiently, as indeed they do. And you can see that even when you do this, the model bias remains. So there is a real ensemble bias here. The CMIP 6 models do tend to overestimate these fluxes as a whole, but there are patterns within this. The GSA8 models show a particularly strong bias. The mushy layer models show a particularly weak one. And in the case of the top melt and the basal conduction, we can tie these differences directly to the thermodynamic model choices of these groups. The IPSL and MRI models are sort of in between these two in terms of the severity of the biases. CMCC and Cinerum Surfax, their CI states are too far from climatology to evaluating this level of detail, but the analysis tells us something interesting. The CMCC model fluxes might look crazy, but they're sensible given the underlying CI state of the model. It is responding in a physical way, whereas Cinerum Surfax, there is actually a model problem lying at the root of it. And we can conclude that although the atmosphere may be the primary driver of CI state, there is a role for the underlying ice thermodynamics to modulate this. And we've got a paper in GMD discussion about this at the moment, which you can see down there, and I'll leave the title up there for a minute. Thank you very much.
Thank you very much, Alex. We've maybe just got a minute or two for any quick questions that people have. Got any at the moment? If not, if you want to pop them in the chat and I can pass them on to Alex after by email, just if you want a little bit of time to read over. So we record these seminars and they are all available on YouTube, but we just ask the presenters. So I'll be asking Alex, CJ and Masa if we can share them. But you can find them all on the YouTube channel, the ones that we've had every month before. And you can also look at our website to find out about the future ones. Stanilo, you got a question?
Yes, sorry, I couldn't find the button, so that's why I couldn't write any question. I'm sorry about that. It was very interesting presentation. I really enjoyed the model the difference between the model parameterization. I think it's very interesting. So I missed one of the models. I missed one, a really main character here is the ECR. So we have three big friends here. We have CMCC, we have IPCL, and we have ECR, They are all good friends, but all of them are very different in the CI representation. CMCC is the poor guy who doesn't have CIs. IPCL is, it's okay, as you said, it's very okay. But ECR has too much CIs. It's extremely thick. The CS volume is about twice the reanalysis data.
That's very interesting. So I didn't evaluate that because not all the diagnostics were submitted. I think that they had a couple of them, but not all of them. So I didn't include that one. Those ones.
The problem is, so CMCD, all of them, I think they use LIM3, and all of them, they use 3.4 NEMO. And all of them have huge theta fluxes toward the Arctic Ocean, about 100, more than 100, when the mean is about 80. So we have a lot of, in particular, across the Barents Seas, where there's a lot of heat. And I observe where it's just I'm worried about the wind stress here, because if you compare the CMCC wind field and the IPCL, you can see that the cell in the Barents Seas is very strong. That's why one of the reasons why the freshwater content it decreases with the warming scenario. And IPCL and CMCC has a very strong I think cyclonic cell in the Barents Sea, so there is a lot of ice going through the fronts. ECR is very thick, but the Bedford Gyre, instead of being in the Canada basin, is covering the whole basin. So I think there is a lot of ice convergence, which actually is piling up the ice and making the ice very thick.
Yeah.
So I'm just wondering, I know the ice parameter is important, but we come back again to the problem of why the wind fields are so different. What we observe. I don't know if you have any thought about this.
I mean, that's very interesting. That's connected to the underlying climate states, of course. I didn't show it in this presentation, but I've got a similar scatter plot of global mean and Arctic Ocean temperature against the ice area and thickness. And these are correlated roughly in the way you expect. And again, the models often cluster in groups. And I imagine that clustering is partly driven by the sort of effects that you're talking about, which are probably related in some way to global and Arctic Ocean temperature.
Mm-hmm. Yeah, actually, it's like I'm puzzled after looking so many models and see so many different things. And
yes.
I don't know what is the issue, and that's why I'm very interested with this type of talks about intercomparison between different model development. Oh,
thank you.
Thank you so much.
Thank you very much. We better finish up because we're a wee bit over now, but Alex, I'll send you the couple of questions that we have in the chat by email that maybe if you get a chance to answer, that would be great, and I can pass them on.